Have you ever noticed that gymnasts always bend their knees when they land? So why don't they land with their knees straight? I know what you're going to say. You're going to say, oh, it's to absorb the impact. But that's a layman's answer. You are A-level student. You need to have more sophisticated language. So the physics involved is the Newton's second law, which says that force is the rate of change of momentum. If we are dealing with impact forces, we tend to write it like this. So the change in momentum divided by the impact duration. Now we're going to throw this delta t over to the other side. So we are looking at F delta t is equals to delta p. Now F delta t looks like quite an important thing, right? So we are going to give it a name. We are going to call it the impulse. The symbol used is usually J. So the impulse, which is F times delta t, is equals to delta p. Now what is the units for impulse then? So since it's a force times the duration of time, it should be Newton's second, right? But it's also equals to the change in momentum. So equivalent units will be kilogram meter per second. So keep this in mind, yeah? So Newton's second is equivalent to kilogram meter per second. It's going to make it so much easier for you to understand. Okay, so what's the impulse needed to accelerate a 2 kilogram mass by 3 meters per second? So that means its momentum changed from 0 to 6 kilogram meter per second, right? So that's the change in momentum, 6 kilogram meter per second. So what's the impulse needed? 6 Newton second. Easy? So this 6 Newton second could be produced by a force of 6 Newton applied for 1 second, or it could be 1 Newton applied for 6 seconds. It could be 3 Newtons over 2 seconds. So it can be any combination as long as the force and the duration of time multiply up to be 6. So back to the gymnast question. So let's say the gymnast just before making contact with the floor was moving at 10 meters per second. So the momentum just before contact is 500 kilogram meter per second. I'm assuming the gymnast mass is 50 kilogram. When the gymnast has come to a rest, its momentum is of course 0, yeah? So the change in momentum turns out to be negative 500 kilogram meter per second. I'm taking downward to be positive. So to produce this change in momentum, what's required is an impulse of negative 500 Newton second. So what is needed is for the floor to give it an upward normal contact force, producing an impulse of 500 Newton second. So what difference does it make whether the gymnast bend the knees or not? The change in momentum is still going to be this. The impulse required is still going to be this. So the change in momentum and the impulse are exactly the same. What is different is the impact force. So suppose the gymnast did not bend the knees. If the gymnast did not bend the knees, then the impact duration is going to be pretty short. So let's assume it's 0.1 second, yeah? So the required impulse of 500 Newton second is brought about by an impact force of 5,000 Newtons over a duration of 0.1 second. But if the gymnast bend the knees, then the gymnast can extend the impact duration to say, let's say, half a second, yeah? In that case, the impulse of 500 Newton second is brought about by an impact force of 1000 newtons over a duration of 0.5 seconds. So again, let me remind you, the impulse is the same. In fact, on the FT graph, force time graph, the impulse is represented by the area under the graph. So these two graphs have the same area under the graph. The impulse is the same, the change in momentum is the same. It's just that by bending the knees, you can spread the impulse over a longer duration of time and therefore reduce the impact force. Now you can experience this firsthand, by jumping and then see if there's any difference if you bend your knees and if you don't. But don't sue me if you break your knees or anything. Alright, that's all. Ta-ta!